Hey everyone, in this video I'm going to go through questions 49 through 54 of the USNCO 2025 local exam. You can follow along with both the exam and the solutions document I've written in the description below. So let's start with question 49. It's asking which molecule among the answer choices is going to be trigonal planar, and we're just going to do some Lewis structures and VSEPR to figure this out. Remember, trigonal planar means 3 bonding groups and 0 lone pairs. So yeah, let's draw some Lewis structures. We'll figure it out. Let's start with NH3. NH3 is going to have 8 valence electrons. It's going to have this type of Lewis structure here. This is not 3 bonding pairs. Well, it is 3 bonding pairs, but it has a lone pair here. That's our answer. Let's move on. NF3 is going to have 26 valence electrons. It's going to have a similar structure to NH3, actually, except the fluorines are going to have lone pairs here, which, that looks like a P, but they're going to have lone pairs here, which doesn't really affect anything. You still have this lone pair on the nitrogen, so according to VSEPR, this is not going to be trigonal planar. Let's move on to C, which is SO3. This has 24 valence electrons, and if you draw the Lewis structure here, you get this type of structure, and that does follow trigonal planar. So our answer is going to be C, but I'm going to solve the rest just to show the process, I guess. ClF3 is going to have 28 valence electrons, and it's going to have this type of structure here. It's a bit of a weird structure because it actually has 2 lone pairs and 3 bonding groups. So it exceeds the octet rule, but that's okay because it's in the 3rd row or below, so it can't exceed the octet rule. This is what you get when you apply ideas like formal charge. So that's our structure. Of course, this isn't only 3 bonding pairs or 3 bonding groups, it also has 2 lone pairs, so it gives a T-shaped geometry, which you don't need to know what that is. As long as you know what trigonal planar is, you know that the answer is C. Okay, for question 50, we are going to draw molecules again. You'll notice that that's a consistent theme in this section of the test, and we're going to try to find the shortest NO bond. So let's start with NO. So NO is a diatomic molecule, and you're going to actually need to use molecular orbital theory to find the proper bond order for this. If you don't know what molecular orbital theory is, I'm going to try to explain it briefly in this, but you're going to have to learn more in depth of what it is for this exam, for future exams, and for chemistry learning in general. So I'll link some ways to learn in the description below, and I'll definitely cover this in some future videos. So let's just get into it, I guess. Remember, this can only be applied for diatomic molecules, and you actually do need to apply it for diatomic molecules to find the proper bond order. If you drew this out, you would get a bond order of 2, which is incorrect. And in fact, the bond order of some commonly known molecules like O2 actually come from molecular orbital theory. So molecular orbital theory is essentially the combination of orbitals from 2 atoms to form a diatomic molecule. So we have nitrogen and oxygen. In this case, they each have 2s and 2p orbitals. So they're going to combine, and their valence electrons are also going to combine. N has 5 valence electrons, O has 6 valence electrons to give 11 valence electrons. So when we do molecular orbital theory, there are sigma orbitals and pi orbitals, and these are pretty much standard. You're going to see that across all molecular orbital theory applications with 2s and 2p orbitals. So as long as you know about molecular orbital theory, you'll know about that, and if you don't, then you should learn about it because I can't really explain that well in this video. So we have this type of structure here, and at the bottom you have low energy orbitals, at the top you have the highest energy orbitals. So the electrons are going to fill up low energy to high energy. So since we have 11 valence electrons, they're going to fill up 2 here, 4 here, 2 here. That gives us 10. So we have 1 left over to have in this orbital. And if you know molecular orbital theory, you'll know anti-bonding orbitals and bonding orbitals or pro-bonding orbitals. And the bond order is going to be 1/2 bonding electrons, I'll just say BE, minus anti-bonding electrons, ABE. And if you actually, I think I covered up the symbols here, but if you erase these symbols, or these lines here, you'll see these asterisks here, which indicate anti-bonding, and the lack of asterisks here indicate regular bonding. So if we just apply this formula here, we get 2, 4, 6, 8 in bonding for bonding electrons, and then anti-bonding to have 1 up here and 2 down here. So that's going to be 3, and this 1/2 times 5 is 2.5. So that's our bond order. I kind of breezed through that. It might take you longer to do something like that, or if you don't know what molecular orbital theory is, you probably didn't understand that very well, but that's okay. If you learn up on it, you'll be able to succeed. So this has a bond order of 2.5. Now let's draw NO2. So NO2 is going to have 17 valence electrons, kind of a weird number of valence electrons to have, but it's going to follow a structure like this. And in fact, it's going to have 1 electron on itself, which is a bit weird, but that's what you get when you apply formal charge and stuff like that. And this is actually going to have resonance because this double bond can go to any of the oxygen atoms. So this is just going to be like a flip of it, technically, kind of. So there's going to be resonance here. You'll notice it has like 2 NO bonds, a double and a single, and through resonance that's going to average out to about 1.5 as the bond order. So that's our bond order for B. Now N2O, it's a similar type structure. I'll draw it down here. N2O is going to have 16 valence electrons, and N2O, you'd think that like this is the only structure. Let me draw it out. You might think this is the only structure for N2O. However, there's also resonance with the form with N having 2 double bonds to oxygen and, sorry, this should be a nitrogen. So there is resonance here. You have a double bond here, a single bond here. So again, you're going to average out to about 1.5. These bond order approximations, of course, aren't exact, but for the scope of this exam, that's going to be okay. And N2O4, this is also going to have resonance, but I'm not actually going to draw the resonance for this one because I think you guys understand the point here. This is going to be 34 valence electrons, so we have a structure like this, with N having a double bond to an oxygen, a single bond to an oxygen, and a single bond to the other N. There is, of course, resonance here because you can exchange these bonds and whatnot. But again, we're going to average these double and single bonds out to get around 1.5 bond order. So yeah, we have 2.5 and 3 1.5s for the bond order for A and B through D. Remember, we're being asked for the shortest NO bond, so we want the highest bond order because bond order and bond length are inversely proportional. So our answer is going to be A. Okay, let's move on to question 51. We're just going to draw the structure out. In fact, it's already drawn out here. I'm not going to draw it out again. There is, again, resonance. Been a lot of resonance recently. But in both the resonance forms, you're just exchanging this double bond here. So the amount of lone pairs is going to stay the same. You don't really need to draw the resonance. But yeah, you have 1, 2, 3, 4, 5 lone pairs here. That's our answer. And this is actually the structural formula. So you can kind of tell the structure of it just by looking at the formula here. You have CH3, so you're going to have this group here, and it's kind of like attached to NO2 here. If you start to draw more Lewis structures and see formulas like this, you're going to be able to identify those structures more easily. But yeah, by just how they write nitromethane, you'll be able to tell the structure and easily find the number of lone pairs. All right, question 52. So this is quite an interesting problem. This actually, the reason why I could solve this is because of Klein organic chemistry. So even though this isn't the organic chemistry part yet, chapter 3, I believe, from Klein's organic chemistry book is pretty helpful in trying to figure out how to solve this problem. But I'm going to explain those concepts here. They're fairly straightforward. It's asking the strongest acid in aqueous solution. So essentially, when you have an acid, if it has a positive charge or a source of H plus that it can easily release, that's generally going to be stronger, because when you want to compare the strengths of acids, you actually compare the strengths of conjugate bases. So let's actually write those out right now. NH4 is going to form the conjugate base NH3. H2O is going to be OH minus. pH4 is going to be pH3. H2S is going to be HS minus. So you want to find the most stable conjugate base, which is going to be the weakest conjugate base, because when something's stable, it doesn't really want to undergo any reactions. So then we're going to have the strongest acid, because the acid is going to want to release that H plus to become more stable, if that makes sense. So when we have an uncharged conjugate base, that's going to be more stable than charged conjugate bases in general. So that in turn means that the acid is going to be stronger. And that seems kind of intuitive, because remember, like, having H plus is generally a good thing for an acid to make it strong. So it's pretty intuitive that we can eliminate B and D. So how do we actually narrow down A and C? We have the conjugate bases pH3 and NH3. So let's go over to the periodic table here. So you'll notice that the only atom by which they change is the central atom, nitrogen and phosphorus, for NH3 and pH3 respectively. So one thing that you should probably know for chemistry in general, particularly in the scope of trying to figure out acid bases and things like that, which is something I learned through Klein's organic chemistry, is that third row elements and below don't really hybridize as effectively or at all compared to second row elements and above. So essentially that means that the nitrogen is going to hybridize effectively while this phosphorus is not. So what that means is that this phosphorus, it's going to have a lone pair in a 3p orbital. This nitrogen is going to have a lone pair in an sp3 orbital, because it hybridizes effectively. And essentially an sp3 orbital is going to be higher in energy, while the 3s orbital is going to be lower in energy. And that means that pH3 is going to hold its electrons more tightly. So pH3 is going to be more stable because it's less willing to undergo those reactions. So that essentially means that phosphorus with its lone pair is going to be stable, or more stable than NH3 with its lone pair. So it's going to be a weaker conjugate base, and thus it's going to be a stronger acid in aqueous solution, or the corresponding acid is going to be stronger, and that's going to be C. If you look at the pKa values, I think it's something like 10,000 times stronger. So it's a pretty big difference, this hybridization thing. It's not something to take lightly when you're trying to understand acids and bases. Okay, let's continue with question 53. So question 53 is asking the 3D representation of SOF2. So we're just going to draw this molecule out and use Vesper to try to figure out what type of structure it is. So SOF2 is going to have 26 valence electrons. And one thing you have to know when you're drawing molecules is that there's a rule that the least electronegative atom has to be the center atom. So if you didn't know that, you've probably been using intuition to draw molecules. But in this case, you might not know if A and B could be correct, but they're not going to be correct because it doesn't have one definitive center atom. And in this case, when you compare S, O, and F, O and F, oxygen and fluorine, are going to have a higher electronegativity than sulfur. So we're going to want to place sulfur in the center. So we can cross out A and B, because in C and D, sulfur is in fact in the center. So now what we can do is draw out the structure with 26 valence electrons. It's going to look something like this. And you'll notice the sulfur here exceeds the octet rule, but that's okay because it's in the third row or lower. So if you're wondering how you kind of get the structure, you know that oxygen prefers to have 2 bonds here and fluorine prefers to have 1. So you can calculate the formal charge of this and pretty much determine that this is kind of how the structure will look. And sulfur wants to be contributing 6 electrons, which it's doing here. As it's participating in 4 bonds, and then it has a lone pair, giving it 6 total. So the formal charges are all going to be 0. So that's going to be the preferred structure of SOF2. And from here, you might be confused because you don't actually see the exact structure in these answer choices. And the reason why is they're drawing the 3D representation. So if we quickly erase this here, essentially, if you consider this structure here, which is trigonal pyramidal, it's going to look something like this. D is going to be our answer. However, sulfur is going to have a lone pair here, which repels these bonds, and this is going to have a double bond here. So this is not showcased in the 3D arrangement of the atoms because that's not the 3D arrangement, that's the structure. And if you look at C here, this is actually implying trigonal planar because these are equally spaced. So this is going to be like 120 degrees, which is not the case if you have a lone pair here, since lone pairs are going to repel the bonds. So D is going to be our answer. Let's move on to question 54. So question 54 requires knowledge of crystal field theory, which is a relatively complex topic. So I highly recommend reading up on it before following along to the solution. Otherwise, most of this won't really make sense to you. I'll link some videos and other like Libre texts you can read to understand the topic a bit better, but I'm going to go through this as if you've at least heard of crystal field theory. I'll try to explain it as much as I can, but again, it'll be really hard to explain if you have absolutely no knowledge of crystal field theory, which you do need to know for USNCO. So let's break this problem down. It's asking which ion is diamagnetic, and we don't really need crystal field theory knowledge to know that diamagnetic means there's going to be no unpaired electrons in the ion. So now we can start to use the crystal field theory knowledge. So essentially, for these complex ions, d electrons determine what the magnetism is, since the s and p electrons are going to be normally paired. So we're going to be looking at the d electrons of the ions, and we can determine that by looking at the metal atom in each of the answer choices. So if we look at the periodic table here and zoom in, we can see that choice A has iron, choice B has cobalt, choice C has nickel, and choice D has copper. So we can just count the d electrons to find the number of electrons that the ion has. So for iron it's 6, for cobalt it's 7, and then so on. I'm just going to label that here, d count of each of these. Okay. Then from there, all we're going to do is apply our orbital splitting. So in these in these fields like octahedral, square planar, tetrahedral, and for complex ions, you're going to have the d orbitals be split into high and low energies. So you do need to know the relative splits. You don't need to know the exact notation like you can see here, but you do need to know the splits and how to determine a complex ion's geometry. So we can see right off the bat that A and C are going to have an octahedral geometry. So we can draw out the split for octahedral. So octahedral is going to have a high, two orbitals be high energy. That's going to be dz squared and dx squared minus y squared. Again, you don't need to know that notation. You just need to know the number of high energy and low energy orbitals from the splitting caused by the ligands. So for low energy, we have these. Okay, and we know that iron's d count is 6. So we're just going to go through and put the electrons in the orbitals. There's two rules you have to follow. The first is that the electrons will fill from low energy to high energy. And then the second is Hund's rule, so they'll each fill one orbital first before doubling up. So let's go ahead and apply that. And we can see that all the electrons are paired in the low energy orbitals, and there's none in the high energy orbitals. So since diamagnetism means there's going to be no unpaired electrons, we can immediately see that A is our answer, which is quite fortunate. So you wouldn't need to calculate or draw the rest for this problem in particular. So we can go ahead and circle A, but I'm just going to show the other answer choices here. So for C, we also have a octahedral field, but its d count is 8. And you might be wondering, oh, that's also an even number, so it's going to also be diamagnetic. However, remember Hund's rule, this is going to fill, but then this is going to fill, and it's not going to double up in dz squared, or one of the high energy orbitals. And you're in fact going to have two unpaired electrons, or two unpaired electrons in choice C. So we can cross off choice C. And as for choice B and D, we're going to see different splits, and I'm just going to go through those. So B is going to have a tetrahedral field. So we're going to see the following split. In this case, it's actually going to have 3 high energy orbitals. And I'm just going to write the notation for that. It's essentially the opposite of octahedral. And for choice B, we have a d count of 7. So let's go through and figure out if it's going to have any unpaired electrons. And in fact, it has 3 in the high energy orbitals. So we can also cross off B. And now let's go through the splitting for D, which has a square planar field. So square planar is kind of interesting because it actually has 4 energy levels. So there's no like high or low, it's just, I'm going to draw them low energy at the bottom, high energy at the top. So the two bottom ones, which are degenerate or same energy level, are going to be these. And then above that we have this, above that we have this, and above that we have this. Remember, you don't need to know this exact notation, just the numbers. And we have a d count of 9. So let's go ahead and fill it up. Remember to follow Hund's rule here. And we're going to have 1 unpaired electron in the highest energy orbital. So again, we can cross off D since we're looking for no unpaired electrons. And like we found in the first showing of the octahedral field, we know our answer is going to be A.